we will continue our discussions on DTMs. So to recollect, we have to process, stochastic process, which we will denote it as Xn. Okay, n equal to 1, 2, 3, so on. Denoting DTMs, where X is the random variable and n is the index or parameter or the discrete time steps. The general notation of X means random variable, but along the index you will have X1, X2 are all separate random variables, and it is a collection of random variables, but it is indexed. That is why we call it as the stochastic process. So what is special about this one? One thing is the time is discrete. Time is discrete, and then the state space, the value taken by the random variable, are discrete. That is why we call it as the chain. And it has this Markov property. We also call this Markov property as the condition property. So, to specify what that property is, suppose we look at the conditional probability that xn plus 1 is equal to I, given that xn equal to j, xn minus 1 equal to k, and so on. That is, given xn minus 1 and some other thing. Need not just be xn minus 1, it can be x minus xn and x minus k, or anything can be given. May also can also be given. And among the different time points at which the random variables values are specified, n is the latest. So we call this as the present state of the Markov chain, and we are making a prediction about the future state, given the present information and the past information. What is the conditional probability that in a future time, again future time, it need not be n plus 1, it can be n plus 3 also. Okay? That it will take a value I, given that j, k and all those three states which it visited at the respective time steps. So this conditional probability, if the Markov property is obeyed, then future predictions depend only upon the present state and not on how the state is arrived. Whether you were at k and came to j, or you were at L and came to j, or all those things doesn't matter. The only thing that matters is this j and where you are going, this I. And because it is stationary, the time steps that is involved. From n you are going to n plus 1. Which means in one time step you are going. Okay. So this is what we call as the Markov property. So if you write it out, it is just probability that x n plus 1 equal to I, given xn is equal to j. Okay. This basically tells that it has no memory. Okay, having come to the present state, it will lose memory about what happened in the past. Every time it is a new one. So if you call this as Pij, because here it is j to I, because you are coming from j to I in one time step. So you can mention it like this. Or you can drop this one if it is understood that you are always referring to one time transition probabilities, then you can as well drop this one and then just write Pji, Kik and all these. So these are important ones. They are called as the one-step transition. Right? Transition, it makes a transition from one state to another state. Probability. Then we also saw that we can arrange these probabilities in a matrix form. So we can have a matrix P, which is an array of PHs. That is called as the state transition matrix. One-step state transition matrix. We can also arrive at multi-step transition matrices. Which are all of the form Pij's of 2. That is, you go from I to j in 2 time steps, which will be, if you look at those probabilities, it will be like from n to n plus 2, we go from I to j in 2 time steps. Unless otherwise mentioned, we always talk about stationary processes, where the transition probabilities depend only upon the time steps involved and not on when the transition occurs. So it is not dependent upon n, it only depends upon 2. Okay. So this is what we are going to talk about. So then we will see that you can have a lot of multi-step transition probabilities, matrices and so on. Finally, this is the one that is important. Using this, all multi-step transition probabilities can be easily obtained. That is what we will see using a theorem called as the where we go from the state I to j in m plus n times. Okay. So what does that mean? Probability that x at time m plus n equal to j given x 0 is because stationary, the actual time doesn't matter. What this implies is the time steps involved, m plus n time steps. Okay, so you can start with an arbitrary time, you call it as 0, and in m plus n steps forward, from I you go to j, from I you go to j with so many time steps. So that is this conditional probability. Okay, now what we can do is, we can now introduce one condition in this place, indicating what state it would have occupied after m time units from 0. Suppose if I do that, probability that xm plus n equal to j and xm equal to k, given that x naught equal to 1. That is, I now want to write this one in a different form. That is, it tells that I go from I to j in m plus n times. This what it tells, I go from I to k in m time steps, and then from k to j in m plus n more time steps. This is what we say. Here what we have done, we have introduced a condition. But actually at the mth time I can be in any state k. All are possible. So you have to uncondition it. If you introduce a condition which was not originally there, you have to uncondition it. So that k can be anything. K is equal to 1 to n. Sorry, not this is, I will just put k. K over the entire, all possible state space. Okay, I will not know, it can be many finite state space or infinite, countably infinite. So because it is discrete, you don't need to put anything. I don't want to use n because n is used for the time scale. So this is just follows from the laws of probability. Nothing new we are introducing. When we uncondition it, you can always uncondition it and you get back the unconditioned. So now again we can use the law of the conditional properties. Now what is this one? You have to put a condition here. So these are conditional properties. But conditional properties obey all axioms and laws of probability, which are obeyed with the unconditional properties. Okay? That is, if we have P of A union B, sorry, is given by PA plus PB minus P of A intersection B and so on. Now we can introduce a condition and then ask all the original probabilities theorems can all be put down. But you have to just put condition, same condition you have to put. Otherwise all theorems hold. Now if you look at it, it is an intersection of two things. Now I can put a condition here and then separate. This is A and B. That can be written as A given B into B, which is this is again just follows from our earlier lectures, just a probability law. Nothing new with regard to this Markov. See, look what you have done is A and B as written as A given B into B. This thing remains. See, this is in condition. Here also it remains in condition. Here also it remains in condition. So we have left it as it is. Don't get what is that? This is keep coming. If you look at this part, that is being written like this. So here, this goes to this side, and therefore you have to separately you have to multiply by this. So now, if you look at this one, if you apply the Markov property m plus n is equal to j, given xm is equal to k and x naught equal to I. So we have information about two times points, 0 and m. M is later than 0. So given information about m, the predictions about m plus n is not going to depend upon x naught. So this is irrelevant, and then so now how can this one can be read it? So this is Pij of m plus n. We look at what is this sigma over k. What is this one? It is from k to j in n time steps. Because from m you are going to m plus n. What we only know, we are concentrating on the time steps involved, the difference in the time. So in n time steps. So that is nothing but P k to j in n time steps, and this is I to k in m time steps. I can rewrite it if you want to, make it look more understandable. Ik in m and kj in n. So the probability that you go from I to j in m plus n is the product of I to k in m and k to j over n summing it over all possibilities. So this is what is called as the Chapman-Kolmogorov equation. To get an understanding of how this can be looked upon, well, now we will just look at the this is the, let us say, the time point 0, this is, let us say, the time point m plus n. So you have, this is time, and these are the states, various states it can be there. So you are originally asking question, at 0 I am in a state j, I, in conditional property, that is m plus n, I am in the state j. I go from this state to this state from 0 to m plus n. This is what I am occupying this state, I should go to this state in so many times. For that, what I have to do is, as time progresses, this process has to be in one state or another, and eventually comes here. There are many ways in which it can happen. From here I can define in I and then go to this, and so on. Finally when it comes here I have to be in J. So it can be like this. It can be in many manner, it can be that, but finally, because I am asking an m plus n it has to be J, finally it has to be J. Okay. So now consider a intermediate time step. What is that? M we have put, right? M. In this time M, it has to occupy one state or another. Supposing it occupies a state which call it as K, then it should have come from I to K and then it should have gone to K to J. This is one way in which it can go from I to J in m plus n times. By first going to K in m and then going to J in remaining m. This is just only one way. But there are many other ways, in the sense that K can take any value. I can also go like this, I can go like this, I can go like this, and so on. All these are different ways in which this can happen. They are mutually exclusive, collectively exhaustive ways of happening this way. And therefore they can all be had. So what is this probability? It is a probability of making transition from I to K. This is what I to K in m time steps. This is K to J in n time steps. So both should happen in order to go from I to J. So you have to multiply it and sum it over all K. So this is what the Chapman-Kolmogorov equation is. Okay. So what it really means is, if you want to get Pij with 2 time steps, it can be written as Pi. Okay. I am just putting m and n both are 1. And this m plus n is 2. From I to j in 2 is I to k into k to j. Each one is equivalent. This is a component-wise theorem of how this can be done. If you want the corresponding, if you want to have this one for all the probabilities, then it becomes a matrix notation. This is nothing but 2-time transition probability matrix. P of 2. All 2-time transitions are there. And each one, this is nothing but one-step transition probabilities. This again, this is nothing but matrix multiplications way of writing, component way of writing it. So, 2-step transition probability matrices can be obtained by multiplying the 1-step transition probability matrix twice. What is this can be written as matrix square, square of matrix, P square. By P square I mean I multiply P by P. See, this and this are different. Here each component is a 2-step transition probabilities. Here it is a product of one-step transition. So we can generalize it and we can have p power m. M-step transition, we have a matrix with all M-step transition probabilities. There can be nothing but it is the mth power of single-step transition probabilities. So all this tells that this is the only matrix we need to worry about. If we have this matrix and the state occupancy at any given time, we can be able to get the state occupancy at any future. Okay. So this is what we look at. So although you find a better way of doing things in the class, can as well do it outside the class. Okay, if you read something or use a laptop and browse something instead of listening to it, can as well do it outside. There is no need to unnecessarily waste your time. Now, how are we going to make use of this one? So suppose we have got, as I mentioned, pi with the state occupancy vector. Which will have elements like pi naught, pi 1 and so on. If there are a finite number of states, n states, so this is the state occupancy. Then if we have this unit step transition probability matrix, then if you want to get pi, okay, this may be the state occupancy at the time 0. So which I will put it like this way. If you want to get the state occupancy at nth time, so what you have to do is, you have to use pi 0 into this p power n. P power n will give you n-step transition probabilities. And from 0th time you can go to the nth time. If you multiply it, you will get the state occupancy probability. Okay? So this is, which means that all state occupancy at any future time can be obtained just by multiplying the appropriate state transition matrix. Now, if you look at this matrix, state transition probability matrix, there are different names that are used. TPM, transition probability matrix. Which is always a one-step transition. Okay. So, these represents probabilities, probability transitions, of course. They are also, of course, probabilities. So, the one property which we expect is that they have to be non-negative. Okay. And in that it has to be less than. So this is definitely it has to be obeyed because it obeys, it has just a represents probability. Then, if you look at this, all these things, what does it take? You are in state 0. This is the property you go from 0 to 0, 0 to 1, 0 to 2, 0 to n. So if you sum all these things, Pij over j varying from 1 to n, this gives probability of going from I to j, where j can be in any one of these two. So if you add this one, this should be equal to 1. Simple reason being, you may be in any state I, but in the next time step, you have to occupy one state or another. So, their probabilities of transition should add up to 1. Okay. So, this way of from I, you have to occupy one state or another, j, which may include I also. You may remain in I, that is also included here. Or go to one of the other states. Those probabilities should add up to. That is another thing that it has to be obeyed for all I. Okay, this is for all possible initial state, this has to be okay. What this means here is that rho sum has to be equal to 1. If we add up the probabilities in the elements in each row, that should add up to. So, any matrix that has these two properties, that is, its element are all non-negatives with values lying between 0 to 1 and rho sum is equal to 1, can be a valid TP, transition property matrix. So we call these such matrices, which are valid matrices to represent TPM for some DTMs, they are called as stochastic matrices. Why it is called as a stochastic matrix is, once you put a restriction on the matrix, any matrix which has this property that the elements are all lie between 0 to 1 and the rho sum is equal to 1, then you don't need to worry whether it is in the context of DTMC or something. It's just a matrix with some conditions. Then by applying matrix algebra, all these things, you can arrive at a property of stochastic matrices. Mathematicians have done all those things. One important thing is, if you have two stochastic matrices, if you multiply it, the product will again be a stochastic matrix. That is why P power n are all stochastic. All of them have to be stochastic matrices. That can easily be checked also. Okay, so this is one important. Another thing, well, we have seen like this one, P pi n is equal to pi 0. Now let's assume a case where we have a discrete and Markov chain which has evolved for a long time, and we assume that its probability, this matrix doesn't change, the transition probability doesn't change. Then if you start from initial state occupancy after very long time, will this state occupancy will it keep changing or will it stabilize? Okay, so if the process is stationary, the state occupancy will also stabilize in the limit n tends to infinity. So we will converge to one particular state occupancy vector in the limit n tends to infinity. Okay. So that is called as the stationary state occupancy vector, because at stationarity, but after very long time, it will converge. And there are many things, we will not get into all those things. Okay, that is this unique, or it can be many, or will definitely will the limit be there, and so on. We will assume a case where that is it happens. Okay, so we can to find out that what will be if there exists a unique steady state occupancy row vector. To find out that, what we have to do is the following. Simple thing is, let us take where L is very large. We know from that equation from n to go n plus 1, you can always go by multiplying by the TP, transition probability matrix. But if it were stationary, this two will be the same, and that we will call it as a general notation pi. So I can write it as so. If I put this condition, I can be able to arrive at pi. We will call it as pi equal to pi into p. So what we are looking for, given p, the TPM of a DTMC, any row vector which satisfies this can be a stationary vector. Because once you reach this one, then it has a property that if you multiply it, you reach a p there. It doesn't change. So it has reached a limiting value, after which it doesn't change. So this it can be used to arrive at the steady state occupancy vector. And what does it also tell? It tells that for the matrix P, okay, this is an eigenvector with an eigenvalue 1. That is another way of interpretation. Okay. So now we will look at certain cases and then how for a DTMC we can get the steady state occupancy and so on. Before that, we will make use of one diagrammatic way of representing DTMC, which is very useful. That is, suppose if you have a case where you want to model a simple weather forecast. You want to classify a day as to be either a sunny day or a rainy day. So, what you have a model telling that given that today is a sunny day, the probability that tomorrow will also be sunny day can be somehow you, by your own understanding of the weather, you can do. And given that it is sunny, tomorrow it can be rainy with some probability, the other way. So, you can come up with a DTMC, which is a two-state DTMC, with two states, one is sunny and rainy, and the probability of given a particular day is sunny or rainy, what is the probability the next day will be sunny or rainy? This is just a guess. Or you may use some weather forecasting model and then also come up with that. But the only thing is, I am trying to arrive at TP. These are probabilities, so it has to be, this has to be a stochastic matrix. I can probably tell this at 0.7, and therefore this has to be 0.3. And then given that it is rainy, probability that the next day it has to be rainy, I can tell it is 0.4, and therefore it is 0.6. So this can be a forecasting model. So you can even enlarge. Suppose, see, today is rain actually in the morning, okay? But what I want to do tomorrow, you will not be able to really tell, because this is the time when those things happen. But if you are given a condition about what happened in the today and previous day, that will help you to predict tomorrow. Because if it is, there is a monsoon or depression that's set up, it's going to rain for about a week before it goes. So you can come up with a case, what happened in 2 days, today and previous days. Yes or yes or yes or R. Do you know what happened, how the day was, the today and previous day. With that you will be able to tell what will be in the next day. But again, you have defined the states as SS, RS and so on. So you have to maintain that state. That is, you have to tell SS means this is today, the same as today, and this is tomorrow. So whatever you have in today has to be present here. You cannot say you are using a window of 1 day and moving it, sliding it, and you are predicting what it is. So if it were sunny today and this has to be sunny, and tomorrow if it is sunny, that probability you will put. If it were sunny, you will not. You cannot go here. You can only go here or here, because what were today here will become previous day and the next day. That is what. So that way you can arrange. So this is a Markov chain in the sense that once you have this one, according to this one, once I know what is today's nature of today, I don't need to worry about the previous day to predict what will be the nature of it. That is what this means. Don't give me anything about what happened yesterday, because once I am here. But that may not be true. If I give more information, I can predict it. So here, this is what this will give. Okay. So this is maybe one thing. Then we will come to, if you have a channel, for example, let us say in communication channel, it will so happen that because of some reason, if you have, one thing is when you transmit bit, the bit may get corrupted. And the probability that the bit gets corrupted, you normally use notation called bit error rate, at which bits are getting corrupted. It may be say 10 power minus 6, means 1 among 10 power 6 are likely to get corrupted. And the channel condition may become sometimes bad, various reasons. If it were a wired line, because of the voltage fluctuations and so on, it may become bad. More often we use a wireless network, that channel state may change because there can be blockage, there can be shadowing effect and so on. In that case, the channel may go to a state where the BER may increase from 10 power minus 6 to 10 power minus 10. Increase in the more errors are possible. So you can model the channel to be in two states. One is good, another is bad. Then you can come up with a transition probabilities like this. Given that you look at the channel state in every millisecond, okay, and if it becomes bad because of voltage fluctuation, it is going to remain so for some microseconds and so on. It will not immediately switch to back to this one. So if it were in bad, it will continue to remain in bad, but it is not all the time. It eventually has to come back to good and so on. So this way you can write a matrix like this one. Good to good, what is the probability and so on. The same thing maybe you can do. But another way of representing is using a diagram. For the same thing, if I use the same thing for also this one, that is, this is for good, this is for bad, good, bad, then the way I could picturize this, if I were in good, I will remain in good in the next time step with a probability 0.7. With a probability of 0.3, I can move from good state to bad state. If I were in bad, I will be in bad state with a probability 0.6 and go to good state with a probability 0.4. So this diagram also has the same information about the matrix, but sometimes more appealing. So this is the diagrammatic representation of the Markov chain. More often we will simply call this itself as the Markov chain. And it is for a discrete time, it is a DTM. So many times we can represent this matrix notation for this. For this one, you will have a matrix, this kind of a diagram with 4 states. Okay? Yes, 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 or yes, or, and then I can have all these kind of things. And so you have to, whatever the matrix you have to put. Right? Is this yeah, you can model it like that. Huh? Again, previous day, but what is important? Present state. My state has got 2 information. It's not club day and this. My present state has information about 2 days together. What I am telling here is that my model is such that if I know this state information, my model will tell what is the probability of going to another state, irrespective of what happened in the previous, in the 2 days from this. Actually it will depend, but I am not going to capture those things in my model. I want to keep the model simple. If I put that way of prediction, then it is a Markov. Now this is how I can represent it. I can have one more thing. For example, let's take a case that you have an urn, U or N. We have encountered it, right? This is nothing but a bag. So this has got to 2 balls. It can be either a red or black. To begin with, we can have 2 balls which may be both red or black. So the way I am going to come up with scheme is that I pick up a ball and then look at the color of it. With the probability of, let us say, 0.8, I will replace it with the same ball. With the probability 0.2, I switch to a different color and keep it. So all the time there will be only two balls, but the color of the ball will keep changing, which is not every time I am going to pick up the ball. Retain the color or switch the color with some problem. So if that is how it is, then will it be a Markov? That is one thing. And if so, what will be the state transition? First of all, what can be the states that we need to know in order to characterize the system? There are two balls in there. The number doesn't change, but their color combinations can be different. So, what are the possibilities of this state? It can be red, red, or red, black, or black and sorry, black. These are the only combinations that can be there. Note that you don't need to worry about what was replaced the last. It could have been the black ball that was put last, or a red ball that has been put. So don't think there can be a BR like just we had the SR and R, Sunny and Wait. Because once the ball goes in the earth, it's totally random. The next time I'm going to pick up, it doesn't matter when the ball actually came. So for the purpose of how it is going to behave, the system will behave based on its state and not on how the state is. So if I know the combination of balls, when I pick up a ball, what ball it is going to be depends only about this combination. If it were this, I will only pick a red ball. For this, I will pick a black ball. Here, with equal chances. So these are the states. Once you get into that state, its future behavior. So once this will also clearly tell. You see, not only I will pick a red ball, with some probability I will retain the red ball or switch to a black ball. So it may go to RR, RB and so on, but that only depends upon this combination. Because the other way of putting it, replacing is not clearly derived out. Okay. So same ball means, let us say 0.8, switch color is 0.8. If this is gone, you know we can easily tell. If it were RR, the probability that it will remain as RR is 0.8. Why? Because I will only draw a red ball and probability that I will retain that color is 0.8. So it is 0.8. Similarly, if it was BB, I will only draw a black ball. Probability I will retain it black, there is a 0.8. So this is also 0.8. So for this to this, yes, I can only draw a red ball here, but I will switch with the probability 0.2. So in which case from RR it will go to RB. So this is 0.8. And how about this probability? Huh? Not here, 0. From red it cannot go to BB because both colors cannot be changed. So from BB I cannot go to red. So from RB to go to RR is important. These things are all to be arrived at. Anything else? Okay, this can also be written. From BB to RB, I can only choose a black and I have to replace it with this also point. This can be easily written. So from RB to RR, that is, I can choose a red with the probability half. Okay, and what I have to do if I choose a red with the probability half, and I can go to B, I am not looking at, I have to come to R, which means I have to choose only black and replace it with red. The probability half I will choose this one. And For replacement, the probability is also 1 by 2, 0.2, sorry, 0.2. That is 2 by 10. That is equal to 0.1. So this will happen at the probability point. This is the only way I can go from R to this. Okay? And how about this one? So this one RB to RB. Okay? I have to choose R and replace R. So 1 by 2 into 1 by 8 times twice. That is equal to 0.2. Okay? And this one can be arrived at, or by summing it should be 0.1 also. So again, so R has to, there are many ways. Okay, I take a bar and replace it with the same bar, I will get this one. Okay, that is the only way. Right. I have to take it and replace it. RB to also BR. Say not, it's not BR, it has to be BB. Sorry, why I am reading it BB. So I have to take Z and replace it the same condition. This is how it is. So this will be the state transition operation. So if I want to find in a long run, okay, how will the matrix be? So what has to be done is the probability of occupancy. I don't know. That is in a long run, after very long run, okay, how will be the state of the system? Then what are the states can be? RR, so this I don't know. I will put it as phi 0, phi 1, phi 2 into this should be equal to louder. Point 1 here. So here what happens? From RB I have to go to BB. The only way is I have to choose this and I have to replace it with black. For choosing this is 1 by 2. I picked a ball at random. And replacing is also 1 by 2. Point 2 by 10. Let's go to point.
How is choosing half?
Huh?
How is the choosing half? I mean, if we are replacing it by another ball, it would become something else.
Yeah. No, what is which half you are talking about? This half.
That half. Would it
No,
be
because
different?
like although I have not mentioned, we have a known units, there are some balls. I picked one ball at random. So any ball in that one is likely to come. That is why there are two balls. So 1 by 2 is the property, it will come, one of the balls will come.
No, but like, if there were two balls,
Yeah.
we picked a red and we replaced it with black. So now the probability of picking a red is 0, right? So
I am not picking up. See, for this event to occur, the only way, see, you are not, see, the only way in which event occurs is to pick. I am only going through that particular event. I have to pick this and replace it. That is the only way I can reach this. I have to pick, I pick this with the probability of and replace it with probability 2 by 10. So this is the way the translation error. You are telling that I can also pick this one. That all will lead to different other things. So this way you can arrive at this one. Okay. You have to solve this basically to get this. So what you have to basically do is that you have to write down this one. Whole thing phi naught equal to 0.8 pi naught plus 0.2 pi 1 plus 0.0. That's it. Then other one is pi 1 is equal to 0.1 pi naught plus 0.8 pi 4 plus 0.1 pi 2. So I will have equations, 3 equations. Okay. And I have to solve. Fortunately, we have one more equation. What is that equation? 3 variables, 3 unknowns only. 3 unknowns, 3 equations. That is enough. But there is one more equation that is. The sum is equal to 1. So apart from this one, pi naught plus pi 1 plus pi 2 is equal to 1. So you solve for this and you will get pi naught pi 1. But by you can easily guess that in the long run, It will so happen the probability that a red ball or black balls are going to be the same. No one is. So accordingly, you can have an RR or a VR, but anything can happen according to itself. So that way you can. There are so many different ways for which this DTMC can act as a model. For example, machine repairman model, where we have got two machines and repairmen. So both machines may be working, or one may be working, one may be repaired. When it goes into repair, it will come back to the working mode by the repairman with certain probabilities, or both may be under repair. So this way is very useful and has been widely discussed in industry and in genetics also. That is, if we have a trait that is present in parents, probably it will go to the offspring itself. And again, it may be passed down further or it may be suppressed at that point. So that is also going very, very widely. So it has a lot of implications and applications in science, engineering, and so on. So we will look at some of the examples. I will give you some examples. We'll start.